already uploaded rest of the videos, so you can go and check if anything you wanted to revise or recall any topic till the last session. Whatever we have done, everything is uploaded. Okay, guys, look here. So today we'll learn and emphasize more on the topic phenols. Check out. When it comes to phenols, there are certain compounds which you must know and their names. Got it? So that's one thing which is very commonly asked here. So the first one being phenol. Okay. Phenol is also called as carbolic acid. Carbolic acid. Okay. And then if you have two OH groups, that is called catechol. Okay. And it should be ortho to each other. If it is meta to each other, okay. If it is at meta, it is called resorcinol. Resorcinol. Okay. And if it is OH and OH, it is called hydroquinol. Okay. Or simply quinol. A typical word quinol will also work. Okay. Now, see now. So next, if you have ortho position with CH3, it is called orthocresol. Orthocresol. This is metacresol. And if it is at para position, it is called as paracresol. If you have three OH groups back to back at 1, 2, 3 positions, that is called pyrogalol. Okay. And I think I forgot to write one more form which is important and we must learn that is if you have OH at 135 position. Okay, this is called fluoroglucinol. Okay, I'll put it. Next, get closer. So next one being salicylaldehyde. Salicylaldehyde. Okay. The other one is salicylic acid. Next one here is called as aspirin. Very important compound. Going ahead, we'll be discussing a lot about that. Then this is phenyl salicylate. Salicylate. Phenyl salicylate. Got it? Now, in fact, aspirin is a common name that we use here, correct? The IUPAC name for that is acetyl acetyl oxy, correct? At which position 2? So 2 acetyl oxy and benzoic acid. Benzoic acid. That's the name which you used, correct? Next one, if there is a methyl here, we call it as methyl salicylate. So it is methyl salicylate. It's all kind of derived from the salicylic acid onwards, right? So there are certain common names for this as well. The first one for phenyl salicylate, we call it as salol, and methyl salicylate is called as oil of wintergreen. Oil of wintergreen. Okay, these are very important common names as well as the accepted IUPAC names. So I suggest all of you can just check it out once thoroughly. Okay. If you haven't have the printout, that's totally fine. You can write it name by name. Got it? You can later update that. Okay, right. Now, look into the preparation of phenols here. So from just a second. Right. See. Let's see the preparation of phenols, starting from benzene. Benzene, if you react with vanadium pentoxide, but keep the temperature up to 300 degrees Celsius, we end up getting phenols. In fact, if you heat it above 450 degrees Celsius, then even these two carbons will break and convert that into maleic anhydride. Okay, and 2 moles of carbon dioxide. So that's the reaction with benzene. Next, Dow's process. Got it? So Dow's process is when you take chlorobenzene. In fact, industrially, this is the one which we use a lot of time. So NaOH in a fused state, which means it does not have any water. It is in a molten form. That molten form, if you react it around 623 kelvins and 300 atm, it will first become a phenoxide ion, and then H3, on adding H3 applies, you'll get this as phenol. Okay. So here the mechanism is mostly benzene type. Okay. So this is benzene kind or benzene type. Let me remind you how the benzene type of mechanism works, where you have chlorine here. Here, such a high temperature, OH minus would be acting as a very strong base, which will extract the proton, push into triple bond here, removing chlorine. So that brings you the intermediate benzene here. So this is the benzene formation. And later on the same benzene, OH minus can attack back to push these electrons away, and we will get this as OH double bond like this with minus, and that minus is the one which will take H plus to convert into O minus and Na plus. Okay, this way. And that on final hydrolysis will give you phenols. Okay, so remember that Dow's process is about using benzene mechanism at a very high temperature conditions. Correct. Now, in case if you have lot of strong withdrawing groups here, so like chlorine with NO2, right, and NO2 if you have, so in that case, now we can use NaOH at much reasonable temperature, so around 300 kelvins here, and just 10 atm. So that would give you OH, NO2, and NO2 this way, correct? Or in case if you have all nitro groups present at 246, then we do not even require NaOH, just the warm water would be sufficient enough to replace the chlorine here with OH and get into this NO2, NO2 and NO2 form. And this is picric acid, correct? This is picric acid, and both goes via AR SN2 mechanism. Here, this is also AR SN2 mechanism. All right. This is the similar phenolic form with substituted nitro substituted phenolic forms here. Okay. Next, look out from diazonium salt how we can get the phenol. Or diazonium salt, if you recall, if you take aniline and treat that with NaNO2 in the presence of concentrated HCl, we'll end up getting a diazonium salt, N2 plus Cl minus, known as BDC, benzene diazonium chloride. Benzene diazonium chloride also, on treating with warm water, it will convert into phenol, okay, plus N2. Alright, of course, plus HCl also. This is the phenolic form which you will get. Here, the mechanism is typically going via ARSN1. This mechanism, if you recall, that means there is a carbocation completely formed on heating, and then water will attack on that unstable phenyl carbocation. Correct? Right. The next reaction is from benzene sulfonic acid. So if you have benzene And then we have sulfonic acid SO3H. Got it? Now, very interesting one here, that is when you use NaOH fused, all of this sulfate will go as Na2SO3, Na2SO4, and give us O minus and Na plus Na2SO4. And that on hydrolysis further will convert that into phenols. Okay. So usually fused NaOH with heat is something which helps in formation of the phenol form here. Okay. Up to this, if you recall, or if you might revise, you will be able to figure out these are all repetitive reactions. We have learned this either as a part of aryl halides or a benzene reactions. Okay. Next, this is an important reaction specifically from phenols topic. My suggestion is all of you write it simultaneously as well. Learn to practice with mechanism. It's very important. Okay. So check it out. How does the reaction work here? So first, imagine I want to prepare cumin. So what is the best process? You take phenol, react with propene in the presence of H plus. It will follow an EAS mechanism to get this into isopropyl benzene. The isopropyl benzene's common name is cumin. And if you take cumin to react with O2, H nu or air, got it? Okay, O2 from air and H nu here. That followed by, after getting that, then you follow this by H3O plus. We will end up getting this into phenolic form, and also a ketone will be coming along with it. This is a product formation. Okay. So how does the mechanism go here? Please check. So from the cumin here, so cumin does have a hydrogen on it, one alpha hydrogen on it. So as you react with O2 in the presence of, O2 in the presence of H nu, so it would form a radical here, and carbon hydrogen will also be forced to convert into radicals. And that O and L, carbon and hydrogen will connect from these two ends. And that will be forming this kind of an intermediate where you have O, and H. So you can see a peroxide is formed from cumin, so that's why it is called cumin peroxide. So we will end up getting a cumin peroxide form. Okay. Now, cumin peroxide, if you continue that in acidic medium here, right? So what would happen here? So first, you would see that we have O, and H with a protonation happening on this position like this. And then the pi bond from here will attack on this oxygen to remove out this water molecule. Got it? So that's how we'll end up getting a three-membered ring here like this. On this case, we will end up getting a three-membered ring with oxygen, and this way with double bond and positive charge, and this H2O will be out. Clear? So we will get this three-membered ring. And now on this three-membered ring, again, when you do protonation, got it? Once we have the protonation has been done, so what do we get here? We would imagine this way, that we will have a protonation being done first. So lone pair will take H plus, right? Sorry, not protonation required because it already has a positive charge. So now water will act as a nucleophile to attack on this position. Okay, on this position here. So that bond will push it to make into that bond will push it to make into, yeah, this bond breaking here. So we'll do one thing, sorry. Let me continue with protonation, then it will be easier to visualize. First, H plus will come here, So we will have like O and H plus two methyl groups. And now water as a nucleophile will attack on this position to remove this part. So what do we get? We will have double bond and plus here. And then we will have this as bond with O and H here. And this side bond has been broken. OH and OH here. And once again, something problem. C double bond of O here. And then yeah, sorry. Bond is not breaking onto this side. I forgot this side. So this bond is breaking to make into a correct double bond form here. So that's why I was not putting out this H plus. My mistake. Wait. Yeah, no, it's fine. Check. So water attacks here, the bond will break here to get back into the aromatic form here like this. And as the water attacks, got it? This bond is still there with the methyl groups like this with OH2 plus. Okay. And from there, the oxygen will take away the H plus coming out from the water compound here to get OH with a plus charge. And that's how it will pull up the electrons. Oxygen will push the electrons to convert this into phenol and ketone. Okay, this is a typical mechanism that you will notice for cumene hydroperoxide method. That's a very important industrial method to prepare phenols. So please look into it once quickly, everybody. Right. All you need to realize is that the oxygen which we have fetched it from air, that is the oxygen which remains with phenol. Okay. The rest of the oxygens which are going on to ketone side, that's coming from water. All good. Done, everybody. Notice this, if there are two different aryl groups on the tertiary carbon, major product is formed by the migration of more electron dense group or more electron rich group. For example, this kind of compound is a starting material. So first you would have benzene with methyl connected with carbon OOH. This is that cumene type of a form, which is peroxide. And then which one needs to be migrated during the process? You have realized that there is a migration happening. Either this is the phenyl which will attack, or this methyl which will attack, or this phenyl which will attack. Out of these three, you need to locate which one is a better migrating aptitude. So if I rate these groups as group 1, 2, and 3, so you would notice that the migrating aptitude, migrating aptitude, that means ability to migrate easily, is 1, 2, and 3. Hence, it is this phenyl part which migrates here, eventually uh, converts that into phenolic group. So you will get this phenol with CH3. So basically paracresol is what you will get, and the second product is about ketone. So this is the ketone which you will get. Then next one. Here there is nitro, phenyl, and methyl. So if I take this as 1, 2, and 3, in that case the migrating aptitude will be more for 2 than 1 than 3. So obviously it is the 2 which is getting migrated. So what, phenol is the one which you will get, and then we have this nitro group on it, on the other phenyl group, like this, connected to C double bond O CH3. So this is the other product which you will get. Next, Dawkins reaction. Dawkins reaction actually is not there for syllabus, but just to get you an idea that instead of the starting material being cumene, now the starting material is benzaldehyde with some substituted groups. So if you have a strong donating groups, then only this reaction is more favorable. Got it? So in that case, the same type of mechanism will take place. I'll just write down the intermediate directly. So you will have a Z here, okay, and then we have this as an intermediate which is forming as C O minus H O O H. This is the type of intermediate which is forming, and from here the migration will take place. That eventually give us product as OH with Z substitution plus other side it will become an acid HCOOH. Got it? Okay. So this follow by hydrolysis, then you will write this as HCOOH. Got it? This is called Dawkins reaction. Okay. Next, from salicylaldehyde here. Sorry. Sorry. From salicylic acid, if you compare, so this is salicylic acid, and I need to convert that into phenol. So for that, the decarboxylation will take place. So CO2 will come out of it, right? So this is a very regular and simple reaction. If you recall that any carboxylic acid, whether it is alkyl or aryl, in the presence of NaOH, you'll get the salt form, and this on strongly heating will give away carbon dioxide and get a minus charge here, which will take H plus from here and get this as O minus Na plus. That on hydrolysis will eventually give us phenol. Okay, so this is typically how salicylic acid can also give you phenols. Okay, next, from toluene. How do we get it from toluene? Toluene, if you react with O2, but in the presence of some copper or manganese salt, in that case also we will get this as OH, and that entire carbon will come out as carbon dioxide after oxidation. No mechanism here, just remember it otherwise. Fenton's reagent is about getting simply OH here from a peroxide, and H2O will be formed here. That's it. Grignard's reagent, see, pH MgBr when you treat with O2. So typically this is what happens. pH MgBr plus O2, phenyl will attack on this oxygen, open up this bond. That gives you PHOO minus MgBr plus, and the second mole of pH MgBr, however, attacks back on this oxygen, breaking this bond, and that's how you'll end up getting 2 moles of PHO minus MgBr plus, which on hydrolysis H3O plus will give us 2 moles of phenols. Okay, so that's how you'll end up getting phenols. This is Grignard's reagent. Next is Elb's oxidation. Elb's persulfate oxidation. That means if you have a phenol, you react with, you know, sodium peroxide disulfate. This is sodium peroxide disulfate in the presence of OH minus, and then follow up by hydrolysis. We will get this as quinols. So this is typically made for preparing quinols. So if you have OH here, right? So in the presence of NaOH, it is in basic medium, so this will remain O minus. And this O minus will basically attack here on the peroxy group. O minus, O, O, double bond O, double bond O, O minus. This is the structure. So the attack actually happens from this end to break this bond here, and the other intermediate what you will get here is O minus, double bond like this. That minus will become double bond here, and then we have this hydrogen with O, SO3 minus. And to retain the aromaticity, that hydrogen will migrate here to get this as OH, ring OH, and that sulfur will come out as, HSO4 minus. That's it. Correct? HSO3. HSO3 minus. So that's how it will release out. Correct? So what we are getting eventually is quinols. Again, this is not part of a JEE syllabus, but very rarely it could be asked like what exactly is ELPS oxidation, but otherwise direct reactions are not asked from this topic. Okay. So the same application is that if you have a beta naphthol and then you want to make it into an OH group here at alpha position, you use the same reagent ELBS oxidation to get this. Alpha naphthol ELB oxidation will come here. Sir, why only these positions? Means at those positions you will have more resonating structures. That's why for beta naphthol, just the alpha position is more substituted form. For alpha naphthol, the para position is more substituted form. Correct? Coming to the physical properties, okay, it is a white crystalline solid. So this is said as colorless in some cases, but my suggestion is you get it as white crystals. Okay, take it as white crystals. And it has a certain phenolic order. Melting point is 43 degrees, boiling point is 181. It is sparingly soluble in water. Okay, it is soluble in organic solvent, most of it. Soluble in NaOH because of the reaction. You can see phenol, which has the pK value of around 10, as it forms water, which is 15.7. So this reaction is feasible. Okay, but the same reaction is not feasible when it comes to Na2CO3. So I can say it is insoluble in sodium bicarbonate, but soluble in sodium carbonate aqueous solution. Correct. Because of its acidic nature, it turns the blue litmus red, while it has a corrosive nature to it. Correct. Guys, these are few pointers you must know about phenols, right? Next, let us see its acidic character. You know that phenol's pK value is approximately 10, which is 9.96. If you react with base, you are expecting it to get water. With NH2 minus, you are expecting it to get ammonia. Sodium electrons will release and try to get H2. R minus will take H plus, convert into RH. Likewise, if you have to react with, let's say, bicarbonate here, okay, So if you have to react with bicarbonate here, expected reaction is that phenol will become phenoxide and we should get H2CO3. H2CO3 in a way is same as writing as H2O plus CO2. Okay. And you know that the pK value of this is around 6.2. Got it? Since it is 6.2, it's very difficult for phenol to generate this stronger acid than him. Okay, so that would not happen. While on the other hand, if you take carbonate here, so that is CO3 2 minus, then expectation is it will become PHO minus and HCO3 minus. And this will shoot perfectly because the pK value is around 12, right? So which means this reaction is feasible. Okay. Likewise, if you have anything like carboxylate here, that is RCOO minus, right? So in that case, this will be expected to form POOH and RCOOH, correct? But because of this reaction as well as this reaction is not feasible because the pK value is around, 4 to 5 here. And next, in case if you're reacting this with sodium hydride, then it will become phenoxide and H2 gas will release. Hmm. And here you can see the pK value is around 15.7, ammonia is 38 and 38. So I can clearly say that feasible, 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 and pK value here is around 48 to 60 alkanes. So highly feasible reaction. This is not feasible. This is feasible. This is not feasible, and this is feasible. So these are the reactions that could probably happen, everybody. Okay. So have a quick look into acidic nature of phenols once. If you were to compare the acidic character, these are all the same things we learned in GOC. Remember, if you have these four groups, A, B, C, D, correct? And I want to make the comparison of acidic character, you will just check out which one is more donating. CH3 is donating, NO2 is strongly withdrawing, cyanide is strongly withdrawing. Out of that, C will be the most withdrawing, then D, then A, then B. While here NO2 at ortho position is very strongly withdrawing than meta because here this will offer minus I and minus M. At meta it only offers minus I. Para also it offers minus I and minus M. So here there is a small twist here. Expected order is that there is NO2 most withdrawing at ortho position, that should be A, then C, then B, then D. But actual order, if you compare, then it is C greater than A, then B greater than D. Why that change has come is due to intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Okay. Where do you see that intrahydrogen bonding? See from here. So if you have O and H here and N double bond O, so this is the hydrogen bonding which happening. Because of this hydrogen bonding, it becomes difficult to remove this H plus. That's the reason why the nitro product, the orthonitrophenol has decreased its acidic character as compared to that of para position. Okay, so these two are some important exceptions that you need to follow. So first C, then A, then B, then D. Next, another very important thing to be noted is that when you have two or three nitro groups present in a phenol, then the pK value decreases drastically. Okay. In fact, if you compare the pK values here, okay, one second. Correct. Check. So if you have HCO3 minus to react with the picric acid pK value is around 1. This pK value is around 8. The minute if you have two NO2 groups, that goes around 4.8. So you can clearly notice that with two NO2 groups, the pK value is drastically changing. That's the reason why you notice when HCO3 minus has been treated with this one, here you will get a positive reaction. That means you will get the product as O minus, NO2 and NO2 with H2O and CO2. So carbon dioxide is released. So you'll get the effervescence of carbon dioxide. While here also you will get the same thing. That is, you will get this as picric acid or picric acid salt here, NO2 and NO2, while the other compound is simply H2O plus CO2. Okay, but the same thing will not happen on this end. You will not get any product. So not with one nitro, we need at least two nitro or three nitro. So you can see which of the following will give positive bicarbonate test. So of course, anything which is more acidic than carbonic acid will definitely give. So one, two, not this, not this, not this. With two NO2, three NO2, this will give you reaction. So yes, even if two NO2s are present at meta position, still they will overpower the acidic strength of H2CO3 and the reaction is found to be feasible. Okay, so that's an important area to learn. That phenols do not give brisk effervescence of carbon dioxide with NaHCO3 unless H2CO3, while dinitro or tinitro will give you brisk effervescence of carbon dioxide. Okay, so I guess this part is clear. Please check quickly. Check. If it comes to dipole moment, having one OH on benzene, of course, because of the electronegative difference, you'll have sufficient dipole moment. With this 2 OH minus, we usually expect that a dipole moment component will be cancelling off each other. Unlike that, basically what would happen here is we'll have O and H with two lone pairs on it like this. Okay, and O and H and lone pair on it. So here, due to the lone pairs, one dipole moment will be here and this component's dipole moment will be here. That makes an overall dipole moment in this direction. So I can say mu resultant is greater than 0. This is what would be observed in the case of dipole moment here. Okay. So that's why we say that in rest all the conformations, right? Only in one conformation, this should show zero dipole moment. That when you have, let me just copy this directly. Yeah. So let me change this direction. So if you have H here with lone pair and lone pair here, so in that case, we will have one dipole moment, one dipole moment component on this direction. And you can see because of these two directions acting opposite, the resultant will be 0. That only one conformation Out of all the possible 360-degree conformation, only at one angle this is zero, but rest all the angles it is non-zero. So on an average, if you calculate, we can say this quinols will have positive dipole moment. Okay, next. Now notice what are all the reactions that are involving, OH bond cleavage here. So first, you would see the reactions. The first type of reaction is alkylation. Okay, so in short, it is O connecting to this R group. Okay, so this is major product here. This is major product here, and this reaction is also, if you recall, called as Williamson's ether synthesis. Ether synthesis. That means we have done this before, if you could recall. So we would have PHOH in the presence of OH minus, converting into phenoxide ion, which is PHO minus, and that when you react with RX, lone pair will attack here, remove this R via SN2 mechanism. SN2 mechanism. So we'll get this as PHOR here. So this is the product you will get. All right. Of course, there are some byproducts also you will see. Byproducts. What is that byproduct is? See, if you have phenoxide ion here, so due to resonance, O minus, so you can see due to resonance like this double bond can shift here, pi bond can shift here. So as you react with CH3Cl here, okay, so this carb anion will go attack on CH3 and remove this Cl here. Hence, we shall get this as O, double bond here with CH3 and H, and that tautomerizes back to get phenol. So we'll get this as phenol and CH3. Okay, but this would be minor product. In fact, it's very specific to this type of solution we are dealing with. Okay, now listen up. In case if you have anything like phenoxide ion here, OH, in the presence of OH minus and something like CH3Cl here in the presence of OH minus. Got it? But it is present in aqueous solution. In aqueous solution, then this product will start gaining momentum and start coming out as major product. So otherwise, if it is non-polar or aprotic solvent, SN2 from oxygen end is more favorable, and that will cause us, major product as earlier. So that means the same compound, if you have to make a reaction in DMSO, okay, in DMSO, then this would be minor, and what will be major product here? So connection from this oxygen end is the major product. That is OCH3. That will be major product. Clear? So I hope the alkylation part is clear, everyone. The same goes with acylation also. That means, if you recall the acylation part, you need to first generate an acyl group, to which we usually take AlCl3 anhydrous, and that will give you Rc double bond O plus RCOO minus AlCl3. Okay, and it is that acyl group which will attach on phenols here. So usually, irrespective of the solvent here, it is oxygen which will always attack here. So that is major. And in fact, hardly you will find any traces of compound coming on the para position and alkylation is being done. That's why no Friedel-Crafts reactions are observed. No. Friedel, okay, Friedel crafts acylation, acylation observe, okay, got it. Same case goes in the next molecule also. You will have like this with phenoxide reacting. So O, C double bond O and R here plus NaCl. Right. Okay. So in case if you take it as NaOH, the chances of coming making a backward reaction is less, and that is called as Schotten-Baumann reaction. Okay, that's called as Schotten-Baumann reaction. Clear, everybody? So please check acylation. Was it happening? All good. Next, check out the other reactions here. With methoxide, the lone pair will attack on methyl. Okay, sulfate will come out. We have come across this before reactions in alcohols. CH2 minus will take H plus. Again, O minus will attack on CH3 to remove N2. We have come across this. These are similar to, not same Williamson synthesis. Similar to Williamson ether synthesis. Now, let's see the reactions where CO bond cleavage is involved. For example, if you have phenol, using zinc dust, zinc will provide electrons onto ipso position. Ipso means this position. At this position, electrons are being supplied. So that help in getting a minus charge. And that minus charge will take H plus and zero. Okay. So this is called ipso substitution. Ipso substitution is taking place in this case. Okay. Next. If you treat with ammonia directly, no reaction, but in the presence of any Lewis acid like Al2O3, in such cases, ammonia will react, correct? Again, an ipso substitution would happen. You'll get this as NH2 here and H2O. This is the reaction that takes place. No mechanisms needed for this, everybody. So just remember it directly. Next, if you compare the halogenation reactions of phenol with bromine in non-polar solvent or aprotic solvent, because there is not much quantity of bromine present as a positive charge, you will get some part of ortho and para bromo substitution here. So this is ortho and this is para. I mean, of course we know that. So I'll write down this as major and minor. Usually ortho is major, para is major and ortho is minor. While if you react that in bromine water, then it will start forming at all three positions, and that will cause this as 2,4,6 tribromo tribromo-phenol, okay, which is a white ppt. This is a white ppt, correct? This is what happens in water. Clear? Sorry, this there is this sorry, next reaction. In the next reaction, you see there is already a CH3 existing. So in that case, you will have to make bromination only at these two ortho positions, that CH3 will remain. Okay. But you got to remember one thing, guys. When it comes to COOH, so let me revise this concept once. Whether you have COOH or whether you have sulfonic acid SO3H, correct? Any of these two you take. If you are pushing them in dilute acidic conditions, correct? this will slowly start losing carbon dioxide. This will slowly start converting into SO3. So carbon dioxide here and SO3 here. SO3 is basically H2SO4 only. Okay. And then this position will take H plus. This position will take H plus. And that is called ipso substitution. And if you mind, please check out this reaction here. When it comes to bromine water, basically we have Br2 in H2O. Br2 in H2O is a great source of HBr plus HOBr. And this is an acidic solution. Okay, so it is a dilute acidic solution which will highly favor the CO minus to eliminate and get the hydrogen on. And that will become the first step. And then continuing the bromination as usual, you will get this as 2,4,6 tribromo. Okay, so that's the important point you need to remember. Same way, bromine water is present here also. So that means you will get this as OH, Br, Br, and Br here as well. Okay. Well, there was a question asked that what if I take bromine first NaOH and then react with bromine water? So of course that will be even more activating ring compared to OH, which is O minus. O minus is even more activating ring. So that will also facilitate bromines to attack on these three positions. Now this was a JEE question which was asked that which of the following intermediates are involved in this reaction? Okay, which means we need to realize how the products are forming here. So please check out the mechanism once thoroughly. So what is happening in this case? The first case is that when you have phenoxide ion here, that is the first intermediate forming. The second intermediate is from the phenoxide ion, right? You are making or pushing towards para position, let's say. That is, we have HOBr here, OH here like this. So pi bond will push here, this pi bond will push here, this pi bond will attack here, removing this OH, thus getting this as double bond O with double bond and Br. So this is one intermediate as well. This is a very stable intermediate. I mean, this is one of the reasonable intermediate which you will get. And the same thing can happen at ortho position also. If you had to attack here at Br and OH, the same thing would have been happened on the ortho position also. You position the pi bonds perfectly. So now notice that this minus charge is pushing, the pi bond is attacking, OH minus is going. So what is the intermediate I'll get? I will get the intermediate as O minus, again on a benzene ring form here. Got it. And sorry, this will have a pi bond here with lone pair of oxygen converted into double bond, and here we have Br and H. So this is the intermediate which is forming. So imagine this type of intermediate forming at multiple positions, correct? So you can have the intermediate, at this position also. So once you get this O minus, sorry, double bond O, double bond with Br and H. So OH minus will take proton from here, and that minus charge will be pushed here, here, and here. And that's how you'll end up getting as phenoxide again, O minus, like this with Br. So this is that phenoxide ion. Imagine the same thing happening at multi directions. Okay, one at ortho, para, and meta. Now come back to the question. This is definitely observed after certain steps. This will never observe two bromines at a time. This we learned it is observed. Meta position will never go, ortho position will go. And this will also be the one of the cases after two bromine addition. So answer is 4 there. So everybody look into it, look into this question as well as the working. In the next set of reaction, in case if you have phenol with a COOH with ICl here. So you would notice that it is I delta plus and Cl delta minus, which means this will act like an electrophile. Hence, the attack would be on the para position. So with respect to OH, at para position you'll get I here and COOH here. All right. Okay. Next, if you have ICL and heat, now there is a slight difference here. What happens is ICL on heating, 2 moles of it will decompose into I2 and Cl2 gas. And when it comes to reactivity of halogens, direct reactivity of halogens towards benzene, right? You will notice that Cl2 is more reactive than Br2 than I2, which means instead of getting iodine as the substituent, now you'll get chlorine as the substituent here. Chlorine will get uh, accepted on the para position. Okay, next, sulfonation. See, if you react phenols with concentrated H2SO4 at around 20 degrees, you will get SO3H at ortho and para position. At lower temperature, you will find this is major and this is minor. This is KCP, this is TCP, that is kinetically controlled product. Why is it called kinetically controlled product? So if you notice the intermediate, what do we have here is OH here, right? Then we have double bond with S, double bond O and OH here. So what you will notice is a hydrogen bond forming, when it is coming out to be SO3 is added, then this is the intermediate which you will get. And during the intermediate, you are getting a stable hydrogen bonding. That's why this will form quickly. So an intermediate which forms quickly, we say it is kinetically driven product. In that direction, whatever the product it forms, it is called kinetically controlled or kinetically driven product. But if you notice the stability wise, para is major or more stable because of its intermolecular attraction. So that means if you have O and H here, so this side and this side, it has hydrogen bonding. And here also we'll have double bond OH. So this side, and this side, all of these sides we have hydrogen bonding. So the total hydrogen bonding forming on a molecule is much more in the presence of in the presence of para position. Therefore, that is TCP. The minute you start heating strongly, you would notice that the KCP will become minimum and TCP will start increasing its content, and that will be major. So that is TCP. This is what you would get. Next, phenol with concentrated H2SO4 in excess. If you put it in excess, then what has been noticed is that sulfonation happens at 2 positions, not at 3 positions, but at 2 positions for 2 reasons. SO3 is trying to deactivate the ring because 2SO3H is sufficient enough to deactivate it. Second thing, SO3H3 as it is a very bulky electrophiles. So 2 reasons. Okay, one, SO3H is strong electron withdrawing groups. Second, SO3H is bulky, okay, it is bulky substrate. Sorry, bulky nucleophile. Bulky nucleophile. Okay, so that's the reason. Now, a lot of times, what is the problem? The sulfonation is pretty much used for, converting this into any product. For example, let me show you this case. If you have OH reacting with concentrated H2SO4 in excess, so the first thing you should get in the mind is that at 2 and 4 positions we have sulfonic groups present now as per phenol. Okay, so once you get this, If you are using bromine water, certainly we will get this as OH here, Br here, Br here, and Br here. So this is the product what you will get. Okay. But now notice this one. Same reaction. Now I'm making a slight difference. Check out. What is the difference I'm making here in this reaction? Instead of directly reacting with Br here, so first I will react this with NaOH. Okay. On reacting this with NaOH, now first you will have OH, sorry, O minus, O minus, okay, SO3 minus, SO3 minus, correct? And then we have, aqueous Br2, got it? Now, in that case, no, sulfonic is a very strong acid to form, so it will not accept H plus that easily. So this time you will end up getting only, you know, one Br at this position, and this SO3 minus and SO3 minus will remain. Got it? So that's the importance that if you want to carry that in basic medium, ipso substitution will not take place. So instead, you'll have this type of reaction happening. Okay. And now if you follow with dilute H plus and heat, dilute H plus and heat. So then desulfonation will happen. So all of the sulfur will go and you'll get one Br only. Okay. So if you want to get only one Br, that too at ortho position, this is a best method. Okay. But if you want to just make only bromines at 2, 4, 6 and or at all positions, then this one is better. Okay. So very important reaction this one is from phenol's point of view. So please do check. This is how the sulfonation works, everybody. How does the reaction proceed with dilute HNO3? See, phenols with dilute HNO3 will give you two products, that is NO2 at ortho position and NO2 at para position, OH and NO2. Okay. The first mechanism suggests that imagine as if the nitric acid is, ionized into NO2 plus, NO3 minus, and H3O plus. So here you already get a NO2 plus directly and benzene will attack. Okay. But you also know that whenever there is HNO3, there is always an impurity of HNO2. So HNO2 will always be present as an impurity. Okay. And there is one problem with HNO2. HNO2 is unstable in acidic condition especially. So it will take H plus from HNO3, convert into H2O and NO plus, and that will convert into H2O plus NO plus. Now NO plus is an electrophile which, either from para position or the position or from para position will attack the phenolic group. That's how you'll get is phenol with NO plus NO. The major product is para. Okay. But is this the product that you will get? Actually, no. Okay. Why? Because once you get this NO here, so this will not be stopped here. Instead, in dilute HNO3, because you are continue to do that in dilute HNO3. Dilute HNO3 is a mild oxidizing agent. It will oxidize the nitroso into NO2. Okay, same thing at para position, which is NO2. So this is how the reaction works if you want to get ortho and para. And as I said, the para is major product in this case. This is the first set of mechanism. See the alternative route. If you directly use NaNO2 and HCl, we know that it will give you NO plus, and that NO plus will come out at this position, para position. Okay, majorly I'm talking only about major product, and that again when you react with dilute HNO3, right? So then we'll have OH and NO2. That's how the nitration happens. What if you take concentrated HNO3? See, as the concentration starts increasing, the oxidizing nature of the acids like uh, nitric acid increases. Okay. So as you keep adding HNO3, right, from the nitrating mixture, it oxidizes the phenols to quinone, which means if you take concentrated HNO3. So instead of getting the product, now you'll get this oxidized version of it, which is quinone. This will be the quinone form. Got it? But does this mean it is the only product? No. You can still get some minor product in the form of picric acid. So we'll get this as NO2, NO2, and NO2. And this will be minor product. This is minor product. Now, to avoid this, phenol is first dissolved in concentrated H2SO4, heated, and then boiled off with concentrated H2SO4. So this is what NCRT also has used, and this is the suggestion from NCRT also. Please use the same procedure, everybody, with concentrated H2SO4. If you may recall, the two sulfonic groups will come into this. And when you react with concentrated HNO3, so because it is in acidic condition, desulfonation can take place. Correct? It will get into decomposition or desulfonation form. So as it gets desulfonated, you'll get OH, NO2, NO2, and NO2. Okay. So this is picric acid. So desulfonation this time would happen because you are putting still in acidic medium, and that's how you'll end up getting 2,4,6 trinitrophenol. Now, importance of this is that it's a very highly acidic organic compound. Okay, so pK value is nearly 1. pK value is nearly 1. Okay, so I hope this part is clear, everyone. Yeah. Now notice. Mm. Next, see. The interesting fact here is, okay, this I have already explained it. In the in the presence of air and light, the quinol will start oxidizing to convert into quinone. Okay. Similarly, not just the phenolic form, I mean phenol form, even if you have aniline, even if you have OH and OH, even if you have OH NH2 and NH2A, in any of these conditions where you have an OH and NH2 position, you'll always get this as quinone form. Sorry. So if all of you got that, check. Next. Friedel-Crafts reactions, whether it is alkylation or acylation, it gives a very poor yield with phenols. Okay, why would that happen? Because it forms a complex with Lewis acid this way, and it will hamper the reaction from happening. Like we have oxygen here, O with H, and AlCl3 plus and minus. So from there, the product need to go. Hmm? So therefore, further reacting with CH3Cl, because it is now withdrawing. You'll hardly see any Friedel-Crafts reactions. Next, anilines will completely, shut down for Friedel-Crafts reactions, and this is again due to complexation of lone pairs of nitrogens. Correct. So now let's go through all the name reactions that are involved in phenols one by one. Okay. Here, wherever the mechanism is needed, I have, put it as important. You have to just go through it, write and learn. Okay. Not now, but later on, when you are practicing, my suggestion is you have to write and learn. Check. First one is a Riemann-Tiemann reaction. Idea is simple. You take phenol, add chloroform with NaOH, and then hydrolyze it. You'll get major product as salicylaldehyde, minor product as para-substituted aldehyde. How do we need to understand here is when you have CCl3H, OH minus will take H plus, convert into CCl3 minus. So this CCl3 minus will be giving away chlorine. So that is dichlorocarbon. Okay. So this becomes a very important intermediate now. So this is an electrophile. Okay. Now, on the other hand, phenol, when you react with NaOH, because you're keeping the medium in basic medium, so it will be first become phenoxide ion. And phenoxide ions are highly reactive. So this O minus will try to push into double bond form. From this pi bond, it will push into CCl2. Right. So check. Once you get a activated phenoxide, so highly activated ring now. So pi bond will go attack the electrophile CCl2 and that will get a charge as minus. And that minus will take H plus from the same position, pushing the link, pushing the pi bonds to convert this into a double bond here. And this will get into CHCl2. So remember, this is like the first intermediate which you got. And pi bond will try to push it. This pi bond has to be pushed out. So Cl will be out again. So that will be the second form of it. The third form is, OH minus trying to find out check out how it reacts on this one. So pi bond is pushed back into aromatic ring form. So this is the third intermediate. Now the last is about O minus as it closes. Double bond will be, mm, no, pi bond will be attacking on this carbon, making into a double bond form. And then this OH minus will again take away H plus internally by OH group here. Right. So once you get this, obviously you can take H plus from here and convert this into salicylaldehyde. That is the salicylaldehyde, everybody. So please go through the mechanism quickly and thoroughly once. In this case, what part is important? Another part which is important is that when you have NaOH been added, it is this chelation of O minus and CCl minus, which helps in gaining the stability more on the para position. Ortho position. So that's why ortho is always coming out to be major product, and it is the same observed for, okay, uh, ortho observed for both NaOH and KOH. In NCRT also they have given it as KOH in some cases, NaOH in some cases, but in both the cases, the major product was chosen as salicylaldehyde. That is ortho substitution only. Okay. Now, in case of OMe already substituted at ortho position, in that case, major product will now shift on to para position. Minor product will be here. The evidence of CCl2 is what if you have a paramethyl here? Then in that case, CHO will get attached on this ortho position, salicylaldehyde will form. That will be major product. But at the same time, there is a minor product which is forming. That is, imagine from the para position when this attacks on CCl2, correct? You are getting this one as an unexpected minor product. And this minor product is an evidence that there must be CCl2 that got attached here. So that's the evidence of the existence of CCl2 here. Okay, so you can see the mechanism also here, how CHCl2 is formed. Okay, next. Remer-Temer's carboxylation. So instead of chloroform, if you take CCl4, correct? Instead of chloroform, if you take CCl4 in the presence of NaOH, that O minus, first the O minus will form, that will push into the ring, pi bond will attack on carbon, one chlorine is removed. So you'll get CCl3. And this CCl3 can be replaced by 3OH minus, and that will convert into COO minus. So CO minus and O minus on hydrolysis will get this as OH and CO minus. That's how you'll get salicylic acid. Okay. Next, abnormal Riemann-Tiemann reaction. These are abnormal Riemann-Tiemann, which means if you take pyrrole, this is called pyrrole, and react with chloroform and OH minus, this will give you alpha positioning as minor product, and this positioning you will get it as, sorry, I wrote the reverse form here, my mistake. This one is major product, this one is minor product. Okay. It has been found that regular Riemann-Tiemann reaction is major product, while there is one more product which is coming minor. Now this time it is beta chloropyridine. Beta chloropyridine. How come this beta chloropyridine is coming as minor product? Please look into it. So when CCl2 is there as it attacks, okay, the lone pair present on carbon can back attack and make a three-membered ring. Now, when would this happen? When the resonance energy is weaker, and you know that pyrrole resonance energy is quite weak, which means less. Okay, so it is less delocalized all the time. So therefore, this pi bond can be directly added onto CCl2 like this. And then the lone pair on nitrogen will push it. This bond will break it, and you will get this into uh, chloropyridine case. And that OH minus can take H plus, and finally we'll get this as beta chloropyridine. So this is the abnormal Riemann-Tiemann reaction. Next, check out Kolbe-Schmidt reaction here. So if you take phenol, react with carbon dioxide in NaOH at around 437 kelvins and 4 to 7 atm, you will get carboxylate here and eventually convert into salicylic acid. So phenol, when you react with NaNOH, so you'll get O minus Na plus, and that if O minus Na plus is there, if O minus has a strong support here, the ring will be highly active and it will attack from this position to carbon dioxide. And again, the chelation is the one which is helping this to form a more stable intermediate. Hence, the para position will always be major. So you will get O minus Na plus C double bond O, right? So connected this way. And we have aromatization regaining back, you will get this compound. Okay. And on hydrolysis, you will get this as phenol and COOH. So this is the one which you need to know. And lastly, phenol, when you react with carbon dioxide and NaOH and H3O plus. So check out next, CO2 in the presence of KOH. This is very interesting, in this case, because both of them are weak acids here. So to favor ortho or para, that depends upon whether you take NaOH or KOH. The bulkier the molecule will become, para will start becoming major. Okay. The lighter the NaOH is present, then ortho will be the major product. Okay. So please look into the Kolbe-Schmidt reaction quickly, everybody. Check how to prepare these compounds. One is aspirin, methyl salicylate, and salol. Okay. First, aspirin. Aspirin is always, generally used as analgesic, which is a painkiller in our body. It is an antipyretic, that is fever reducing drug. It can be used as anti-blood clotting. So this aspirin is always used as a first aid whenever heart attack comes. Okay, so you can see that will help in declotting the blood here. So next, if you see phenol and COOH are present here on a salicylic acid, then this OH will attack on the acetate group. Okay, sorry, uh, uh, anhydrate form here. So I wrote this wrong. Let me rewrite this part. Anhydrate, which is CH3, CO twice O. So if you take an acetic anhydride, so the lone pair from this oxygen will attack, make an esterification. So due to esterification, you will get an acetyl group here. So this is acetyl salicylic acid, or simply you call it as 2-acetyl oxy benzoic acid. So it is aspirin. Next, methyl salicylate. When you use methanol, now this acid and alcohol together will make an acid-base reaction. So you'll get this as methyl salicylate. Methyl salicylate, also known as the oil of wintergreen, which I told you, it is mainly used as a pain balm or a spray, release spray, or uh, the pain killing sprays which you have, or Jendu balm, if you remember, Moo, okay, Volini, all of these kind of ointments, these all have methyl salicylate in it. Next, Salol. Salol is this compound where when you react with phenol, again an esterification happens between acid and alcohol here. So that converts into phenyl substituted salicylate, and that is used as an antiseptic, whether it is Dettol, Savlon, in all of that, we'll use it as Salol. So that is phenyl salicylate. So these two are important preparations. Please make sure that you are aware of how aspirin, methyl salicylate, and Salon is been prepared. Simple EAS reactions. The next one is preparation of phenolphthalein. Okay. So 2 moles of phenol when you make an EAS reaction on phthalic anhydride. Okay. On phthalic anhydride. So then that will convert into this compound which is phenolphthalein. Okay. So check. In phenolphthalein, first it will take H plus at this position, right? In concentrated H2SO4, and this carbon now will be active enough as an electrophile. So phenol attacks from the para position to first get this product. Again there is OH, so that OH will get protonated. So second mole of phenol will attack. As the second mole attacks, you will get this compound here. Okay, clear everybody? This is the compound you will get. So check out the degree of unsaturation. 4, 4, 4. So 12, 13 and 1, 14. So total 14 is the degree of unsaturation of phenolphthalein. And phenolphthalein, as it forms, you can see if the pH is less than or equal to 8, it remains colorless. And if the pH is greater than 10.5, it will remain colored. What colored? Pink colored. So phenolphthalein appears pink color. Okay. Now phenolphthalein as an indicator, it is a weak orange organic acid, and this OH minus, as it takes H plus from it, the OH minus will keep pushing itself to get into this quinoid form or a non-benzenoid. So this is not a benzenoid. This is benzenoid, but this is not a benzenoid. Even if one ring is non-benzenoid, we call it as quinoid form. Okay, and it is that quinoid form which gives a pink coloration. And in the presence of excess of strong alkali, even that OH minus will back attack, pi bond will go. Again, it converts into benzenoid. The minute you get benzenoid, again it remains colorless. So, phenolphthalein at an extremely high basic solution, like pH very close to 40, in that case also it remains colorless. So, the best range of phenolphthalein is somewhere between 10 to 13. Okay, between that range, you will have a better coloration or better pink formation from phenolphthalein. Okay, next one. The same reaction, instead of phthalic anhydride, if you take acetone and make 2 moles of phenols to react, so then you'll get this as bisphenol acetone, BPA. BPA is a cancer causing agent. So that's why if you see these bottles, the water which I'm drinking, all of them are been mentioned as, BPA free bottles. Okay, bisphenol acetone free bottles. Next, Lederer-Manis reaction is not there for you syllabus, so and also we discussed that in polymers. So as of now, I'm not touching that. Just I'll keep it in your notes for your reference. We'll come when we come to polymers, we'll discuss that. Next one is Lieberman nitroso test. So in Lieberman nitroso test, what you will get here is uh, when you react with HNO2 or NaNO2, first nitroso compound will come. And nitroso in the quinoid form appears green color. Okay. And then when you react with one more mole of phenol in acidic medium, so this is a compound which you will get, which is called indophenol. Indophenol is red in color. And that when you take it with NaOH, OH minus will take away H plus and convert into this color, which is blue in color. That's what is called GRB test or Lieberman nitroso test. Okay. Yes, generally secondary amines will always give you yellow coloration that we'll go and learn in amines. Okay. But please make sure you remember what is endophenol, especially endophenol color has been asked multiple times. Endophenol is red color, and what is the degree of unsaturation also? You can see 1, 2, 3, 4, 5, 6, 7. 7 pi bonds, 2 rings. So 9. So degree of unsaturation is 9. Next is Fry's rearrangement. Okay, that is if you have an ester form on benzene here, correct? So with AlCl3 and heat, so you will see this will become a phenol and this C double bond O R will connect on ortho or para position. This is a very exceptional reaction where the TCP is ortho and KCP is para. Okay, and this TCP is is explained on the basis of strong hydrogen bonding, intramolecular hydrogen bonding here, right? As compared to that of this one will have some bonding intermolecular, but not as great as that of ortho position. That's why thermally this is more stable as compared to thermally this one. Okay, follow through the mechanism. Oxygen takes AlCl3, creates a positive charge that pushes the electrons towards oxygen. Correct. So removing this as C double bond OR. C double bond OR is an new electrophile here. So that can attack on ortho or para positions. So from here it can attack, convert into this major product, and from para position it will convert into this minor product. So this is a product based what you will get from Fry's rearrangement. Next, diisocoupling. Diisocoupling is when you have phenol reacting with diazonium salt. Okay, so you can see this is benzene diazonium salt, and at around pH 8 to 10, right? Ice cold. I mean, temperature has to be ice cold so that you can get a better azo formation and orange color dye is formed. See the mechanism in slight basic medium. 8 to 10 is a mild basic medium that will activate the ring because it will become phenoxide, and then it attacks from the para position to diazonium salt, which will act like an electrophile, and that comes out to be C double bond O here. You'll get this quinoid form, right, with N double bond N and pH. And OH minus will take away H plus, double bond will move, pi bond will move here, and you'll get this as O minus. And this O minus will take H plus from the aqueous solution and finally convert into orange dye form. Okay. So remember, this is called diisocoupling reaction. Very important, asked very frequently. Correct. So learn that. So you can see color is due to the extended conjugation. Diazonium salt is only stable only stable below 5 degrees Celsius. Above 5 degrees Celsius, it will break into phenyl. And, phenyl carbocation, phenyl carbocation is highly unstable, but still above 5 degrees it forms. And from there, you can get various products. Next, pH N2 plus is a weak electrophile and normally attacks at the heavily reacted aromatic compounds like phenols and anilines. Okay, so this one will be NO2 OMe here is not activated. NH2 is highly activated, OH is sufficiently activated, so you'll get dye formation. But if you have OMe, it will not activate unless you have at least two NO2 groups on diazonium salt and its electrophilicity is increasing. And because of this electrophilicity, now you will notice that this uh, uh, phenol end will attack on nitrogen's end and that forms a dye. Different color dyes here. Okay. So you can see this is the extra information that how do we increase the electrophilicity? More withdrawing groups, more electrophilicity. What if your pH value is greater than 11, 12, and so on? As the basic character increases on diazonium salt, this OH minus will attack, pi bond will shift, and this is the product what you will get. And this is like an acid form known as diazotic acid. Next, this reaction does not involve, one second, just a second. In case if the reaction is being done by beta naphthals, right? So the same type of azodie formation, but this time at this alpha position, the attack would happen, and you would start getting the red azodie. And if it is from alpha naphthol, the attack would happen from the para position, and you will get this type of formation. So all these are azodie formations. Now these three colors you better remember: red, orange, yellow. That is for beta naphthol, it is red color. For phenol, it is orange color. For aniline, it is yellow color. Okay, so that's easy way to remember it. So please do check. Clear, everybody? Right. Okay. So please check this reaction quickly once. What is Gatterman, Koch, and Gatterman? This is an old reaction. We have done it in benzene already. So just go through it once quickly. Gatterman, Koch, and Gatterman reaction. The Gatterman reactions typically has, dry HCl in the presence of AlCl3, the presence of AlCl3. So lone pair from oxygen will attack here. So to come out as AlCl4 minus, and that's how you can get an electrophile C double bond O plus. And that's the position where from all alpha position it will attack. And eventually you'll get this as salicyl aldehyde. Gatterman aldehyde synthesis. This is called aldehyde reaction or synthesis. So you can take it as HCl in ZnCl2 or AlCl3. Both are fine. Same type of reaction. Instead of C double bond O, now you'll have C double bond NH. And pi bond will attack on it. You'll get imines. Imines on hydrolysis will get this as aldehydes. Okay, so these two reactions are old ones. I'm sure you would recall them. Photofry synthesis about OC double bond O R here. Same thing. We can get OH and COR, and it can give it ortho position as well as para position. Correct? Usually in this case, para is major product. Okay. Finally, these are the tests of phenols, everybody. So remember, first sodium metal test, that is phenols will give H2 gas. It will give blue to red litmus coloring. Neutral FeCl3 test. This is very important that Fe plus 3, when phenol is added to Fe plus 3 salts, it will give a violet coloration. In fact, depending upon various type of phenols, it can give red color also, red, blue, yellow, orange, different colors that way. But idea is we need to have an enolate ions, enols. So if the enol content is greater than 30%, usually, okay, sorry, not 30%, 10%. Even if you have greater than 10%, you will start getting this as product. So this even beta keto ester, for example, we have double bond O, and here we have double bond O and OET. This will also give positive test, positive test, positive test, because all of these will have sufficiently high enol content. Okay. Bromine water test, white PPT formation, we have learned that. KMNO4, it decolorizes and turns everything into brownish color because quinones are brown color. And CAN test also converts into quinone, which is brown color. Livermin nitroso test, we learned that it is GRB test, correct? Which is red color changing to blue color. This green is not usually registered in many questions. They usually ask for red to blue. That is indophenol to indophenyl oxide. Okay, right? So these are the tests for phenols, everybody. So these are some important uh, reactions, name reactions, which you need to follow. My request is please go through these reactions once thoroughly, correct? Write and practice. Okay, otherwise you'll forget very easily. Wherever I have put that star marks, it's very important to go through that and make sure you practice it multiple times.